Hey, welcome back to the channel. Today we're going to be talking about a really active area of research in astrophysics that also happened to be the topic of my master's dissertation. That's right, today we're going to be looking at black hole mergers and their role, potential, in solving the crisis in cosmology. Dun dun dun! Before we begin, I would really appreciate it if you like my content that you like and subscribe to the channel. I make a lot of astrophysics and cosmology themed videos, and I try and make topics that are usually quite high level as easy to understand and as fun as possible. We also like to get really crafty here as well, so if you like those two things, then I definitely recommend you subscribe. Right, so this video is going to be structured a little bit like my dissertation report, where we're going to first off introduce the Hubble Tension, also known as the crisis in cosmology. Then we're going to go into very briefly some of the current techniques and methods that we've got, and then I'll also introduce the technique that I was looking into, my methods, very briefly, and of course my results and what we found out. I actually think this was probably one of my favourite projects I've ever done so far. In fact, I loved all of my fourth year research projects, so I'm really excited to get into this one. One of the biggest problems that we're facing in cosmology is determining the rate of expansion of the universe, which we call Hubble's constant. This problem is arising from the fact that with the different techniques that we have, we get estimates that are actually their disagreements are statistically significant, and with improvements to equipment sensitivity, we're finding that this disagreement is actually just being exacerbated further. Statistically significant usually means that we're rejecting the null hypothesis, so that what we're measuring, like our results are just just natural chance. This is usually the definition that we have in most of research. So for example, if we were measuring, I don't know, lupus, and we find that in most cases it occurs around 5% of the time, plus minus 2%. I don't know if that's actually accurate to real life. I just thought of that was the first thing I thought of. If we know that it's 5% plus minus 2, that's 3 to 7% we expect, including errors. And so if you take a sample and you find that you get 6%, well, that's perfectly fine. That's within the error range. We don't expect anything weird going on, so we accept the null hypothesis. Wehowever, if, I don't know, you took a sample of people who ate chairs for a living and you found that they get lupus 90% of the time, then clearly we're rejecting the null hypothesis, and something about eating chairs is making people get lupus more. I don't know why I thought of these ones, but that's essentially what's going on. So in the case of Hubble's constant, we've got these lovely estimates and their errors, but these errors don't actually overlap, which is what you'd want if you want to, find like a middle point, or accept the null hypothesis that there's just a little fluke in our measurements. We've got these really big gaps, which is why we say that our results are statistically significantly in disagreement with each other. But the problem is we don't actually know what's causing the gaps. So analogies aside, we have big disagreements in our estimates, but we don't know why. And what's even worse is, because we don't know why, we don't actually know which of the results, or if any of them, are actually any good, or if just all of them are rubbish results that are all being affected in their own unique ways, which, is likely. So we've got quite a few different methods and techniques to estimating Hubble's constant, but they can mostly be split up into two bins: direct methods and indirect methods. Of the indirect methods, I think CMB, so cosmic microwave background measurements, are by far the most popular, and it's the one that I hear about most. In this method, we're not actually, measuring how far away things are, receding from us, which is the expansion of the universe itself. Instead, we're inferring it from early universe properties within the CMB. I'm not actually sure on exactly how the physics works, but essentially what scientists do is they just measure the anisotropies in the CMB. So you know how it looks all mottled and stuff. You just want to measure how big these fluctuations are and how many we've got. And from that we can infer from these properties the Hubble's constant. So I don't remember all of the estimates by heart. I'm very sorry about that, but I've got them here from my report. What I've written essentially. So measurements from the South Pole telescope, they estimated Hubble's constant to be 68.8 plus minus 1.5 kilometers per second per megaparsec, which is an interesting unit, I know, but that's how we do things here. in combination with Planck data. So I took all of the estimates and just found the best, the most representative one. The most comprehensive and constrained estimate is 67.49 plus minus 0.53 kilometers per second per megaparsec. So it's actually quite low compared to the other ones, which we'll get into in a second. Now, conversely, direct methods actually measure expansion itself, and so they make use of Hubble's law, which states that the recessional velocity, v-rec, or just v, is proportional to the distance, so how far away something is from us, with Hubble's constant being that constant of proportionality. So essentially v equals h naught d. That's how we write Hubble's law. And you can actually see why how the weird units come about, because if you rearrange it to h naught equals v divided by d, you get v, which is in kilometers per second, divided by d, that's per megaparsec, so that's where we get the weird units from. In order to measure recessional velocity, we just use a very simple relationship between that and the redshift of a source, where v equals, I think it's the speed of light multiplied by the redshift, so v equals cz. So all in all, we only need two fairly measurable properties to be able to estimate Hubble's constant, the recessional velocity, which we just take from the redshift, and then we've also got the distance, which, yeah, that's where the problem tends to arise. Most estimates use type 1a supernovae because they have a really good and strong distance to luminosity relationship, plus minus a bit of error, and those distances are calibrated from Cepheid variables, or the tip of the red giant branch. These objects tend to be a lot closer to us, so once we get their distance, we can then calibrate that to something further out, like the supernovae, which usually we see in other galaxies. A recent estimate with the TRGB, tip of red giant branch, as a calibrator found Hubble's constant to be 72.1 plus minus 2 kilometers per second per megaparsec, so it's a bit higher up than the the CMB estimates. However, when it comes to Cepheid estimates, they tend to be slightly higher, and the most recent one that I could find had an estimate of about 73.3 plus minus 1.04 kilometers per second per megaparsec. So you can actually see with that last measurement, 73.3, if you take away that 1.04 as to get the lower bound of the estimate, it doesn't actually match up to the CMB measurement, so you can sort of see the discrepancies already. Before we go on, I should mention that we do have some other new techniques that are hoping to enrich the pool of estimates apart from my own. For example, one of them I believe are Mira stars, which are low mass red giant variable stars, which will either replace Cepheids or the TRGB in supernova estimates, basically. What's great about them is that you can find them in a lot of abundance within not just the disk of a galaxy, but the halos of galaxies if they have them. So because we see quite a lot of them, they could be quite favourable. So I was tasked to investigate the standard siren technique, and this technique actually uses gravitational waves instead of electromagnetic waves to measure distances. The standard siren technique actually uses binary black hole mergers in galaxies, and they're emanating gravitational waves in order to measure distances in lieu of supernovae measurements and all of their calibration stuff. We just get rid of that, push it out the window. Events involving really heavy, compact, massive objects that are accelerating, so for example the merging of black holes or even some neutron stars, they will transport away a lot of that energy as they're spiraling into each other in the form of gravitational radiation, which we pick up as gravitational waves. So if their separation is decreasing and they're spiraling faster and faster together, they're actually losing energy, and so in order to conserve energy, they actually just emit it out in the form of gravitational waves, which we pick up. This phase of the merging process is called the inspiral, where they just get closer and closer together and they begin to merge. Once they actually get to the ISCO, the innermost stable circular orbit, that's about as far as these two objects can orbit each other in a stable orbit, is kind of labelled in the name. But once they reach that point, they start to begin the merging process where they actually come together. And then after that, I'm not really sure about this stage itself. I think it's an interesting stage. We get what we call the ring down. So once the merging actually completes, the black hole will sort of vibrate, if you will, a little bit, and the ring down is the damping of these vibrations as the newly formed object settles. The reason we don't look at supermassive black hole mergers is because the timescale for these are just too long for any human to measure, so we'll never be able to get any useful information from the merging, gravitational wave signature from these. Things that actually have a measurable timescale have to be stellar mass black holes, so these are usually above 25 solar masses. So gravitational waves are an absolute goldmine of information if we can tap into them properly. They preserve key information on both the individual objects' masses, their separation, and most importantly, their distance from us, which is what we want to figure out in the purpose of estimating Hubble's constant. What happens is with each merger, they actually exhibit a very similar chirp. There's the same sort of shape of the chirp, which you can probably see. I'll pop up a picture of it as well. The gravitational wave signature decreases in amplitude with distance, but the actual size, the shape of the chirp doesn't actually change at all. So if it's closer by, it's just bigger in amplitude. If it's further away, it's just smaller in amplitude. So if we know that, and provided there are no other sort of influencing factors, which I don't think we have, if you just compare it to like a standardized chirp, you can get the distance out pretty easily. That's pretty good. We have, essentially the distance part of Hubble's law sorted. All that we need is just the recessional velocity. With one detector by itself, you can't actually determine the location of a binary black hole merger or just a gravitational wave event, but with multiple ones, you can actually triangulate the location based on the time delay, which is quite interesting. So I think currently triangulation is done using both detectors at LIGO, so LIGO Livingston and LIGO Hanford, is it? I think my American geography is terrible, and also the Virgo detector, which I believe is in Italy. One key thing to note is that black hole mergers aren't expected to produce any measurable lights by themselves. Neutron star mergers, which are from neutron stars as opposed to black holes, might be able to, produce some electromagnetic radiation, which we can pick up. But with black holes, we don't expect that at all. So why the location and the distance is important is we can sort of pinpoint where roughly in space it is, and from that we can assign it to a host galaxy. So hopefully our measurements are good enough that we can find it's a galaxy next to it, or that it is within, and then assign that as the host galaxy and take the redshift from that. And from that we can get our recessional velocity. We've already got our distance, and therefore we can make an estimate on Hubble's constant. In real life, it is a lot more, difficult than this. There's a lot more processes going on that we need to obtain Hubble's constant, but this is quite a nice simplified explanation, I think. Why do I actually think this would be any good? Well, I think what's great about this technique is that it's very independent of the other direct methods that all sort of are based around supernovae measurements, whereas we're not looking at electromagnetic light with regards to the distance aspect of this technique. We're looking at gravitational waves, which we hope don't have the same sort of biases as, electromagnetic light does. You've got things like dust absorption, especially with blue light as well, which can affect our results pretty badly. And we've also got things like the Malmquist bias and other biases as well when it comes to light that, really do skew our results. However, we're expecting and hoping that gravitational waves don't have the same sort of problems. Right, so for the last part of this introduction and theory section, and I know this is quite a big section of my report, so I'm sorry about that. We're just going to quickly go over some of the current limitations with regards to the uncertainties, and we'll just talk about some current estimates that we have, which, yes, we do have some estimates. So in terms of distance measurements from gravitational wave detectors, I believe we expect a roughly 25 to 30% error on the distance. So if you get a distance measurement, it's plus minus 30%. For the purposes of my report, I used the larger end of this error, so I did plus minus 30%, and that's just because I want to get a worst case scenario sort of. I don't know why I did a worst case scenario, but I just decided to do that. In terms of the location on the sky, most estimates have errors that are represented as what we call a 90% credible region. You'll see it written as capital C, capital R, and then in subscript it's just a 90 or 0.9. And this represents the patch of the sky where you have a 90% chance of finding the merger. You'll have a point in the sky where you get the estimate, but then there's just a little blob around it. Usually it's actually hot dog shaped as well. The credible region, the 90% credible region, has decreased quite a lot with each observing run, of which there have been 3, and we're currently going through the 4th one right now. In observing run, our uncertainty range was typically 460 to 530 degrees squared, which, yes, that is a lot of the sky, but you know, that's completely understandable with your first observing run. For observing run 2, I think it was 230 to 320, which is quite a big decrease as well. And then for O3, observing run 3, the range was 120 to 180 degrees squared, which is a much bigger improvement compared to observing run 1. I think for the current observing run, they're hoping, depending on how many detectors they can get up and running, you know, within the next decade, we should see a decrease, potentially even down to, I've seen 9 degrees squared, but that is one of the most optimistic scenarios. I really don't think we'd ever be able to get it down that far within, you know, a couple years. But I think it should hopefully be around 100 or potentially even lower than that, which is pretty good, I'd say. For the purpose of my report, I used observing run 3's range, but I just went right down in the middle at 150 degrees squared, which is, you know, quite a nice round number. So in terms of estimates, yes, once again, I can't remember all of these off by heart, I'm sorry. I think the first one was gravitational wave event 170817, which we believe is actually the gravitational wave counterpart of a neutron star merger, which was detected in 2017 by LIGO. So this was quite a rare event as well. I'm really glad we got to capture this. We were able to figure out the host galaxy, which we believe is NGC 4993, and we were able to get the recessional velocity from that. So once again, with neutron stars, we do expect them to have some electromagnetic, you know, wave, you know, produce some light, but it's not exactly confirmed, and especially if they're far away, it's not going to be easy to detect that. The final estimate for this one was, for Hubble's constant for this, was 70 plus 12 minus 8. So with these errors, we actually have them asymmetrical, so you can't just say plus minus 2. They're actually much larger on the overestimate side than the underestimate. So we've got 70 plus 12 minus 8 kilometers per second per megaparsec. And this actually fits quite snugly within the CMB and the supernova measurements. The value itself is quite literally in the middle, and of course the errors, they're quite large, so they encompass everything, which doesn't really tell us much right now, but you know, with improvements to equipment and stuff, we should hopefully see some better measurements. Following that, I found another estimate which found Hubble's constant to be 75.2 plus 39 minus 32, which is roughly plus minus 50%. It's quite large, but they did use a flat uniform prior to estimate their errors, which this is all Bayesian statistics, don't worry about it for now. For this one, they used the luminosity distance estimated with gravitational wave 170814, and they found a redshift using a nearby galaxy using the dark energy survey. The most recent estimate that I found at the time of me actually gathering my information was gravitational wave 190412, and it used a similar method, and it found Hubble's constant to be 77.96, which is quite high, plus 23 minus 5.03. So at least with the underestimate, the lower ends of the error itself, we're seeing a slight decrease in the amount itself, which could be quite good. But this is actually quite a high estimate as well, so that's quite interesting. So all in all, these estimates are quite good in that they align very closely to the other two methods, so with the CMB and with the supernovae itself. They tend to be a little bit on the higher side, which is quite interesting. You'd think that that means that they'd be more, this would mean that the supernovae measurements are sort of more accurate to real life, but that may not necessarily be the case. What's interesting is that we're seeing that the upper bound errors are much larger than the lower ones. Sometimes, you know, with the 5 and the 22, that's like 4 times greater, which is quite interesting. But we believe the reason is that this comes from the part of the method where you're assigning the merger to the host galaxy. And, you know, in the universe, there are more galaxies further away from an event than there are closer by, and so the probability of it being assigned to a further galaxy is much higher than a galaxy that's closer by, and so it would skew Hubble's constant to be slightly larger in that case. Put a pin in that because this will come back later. For the data, I decided to pick a simulation. I picked the Eagle simulation, which I cannot remember what it stands for, but it is essentially used to test out cosmological parameters and stuff. It's quite accurate to actual position of galaxies in the universe up to about, I think, 400 or 500 megaparsecs, and I only use galaxies up to 100 megaparsecs, so it's really great for that, and you know, that's all I needed it for. It also it generated and simulated the galaxies based off of CMB properties. So in this case with the simulation, they've generated these galaxies based on Hubble's constant being 67.7 as opposed to, I don't know, like 73, 74. The larger estimates from supernovae. This is going to be important as well later on. And I know what you're thinking, like, why not just use real galaxies? Why are you basing it off of estimates that may potentially be incorrect? And that's a good question, but I'm not actually trying to get an estimate of Hubble's constant using this technique. I'm actually just trying to test out the technique and see how robust and how, you know, reliable it is, how well it will work to give me Hubble's constant, or you know. So the reason that I picked it is because I want to be able to compare my own estimates with, you know, the true value of Hubble's constant. And if I use a simulation where Hubble's constant is known, then I know exactly whether or not I'm overestimating, underestimating, or, you know, how far off I've gone, if I've made any really large mistakes or whatnot. So it gives us quite a unique advantage in that sense. So for the method, this takes up around 10 pages of my report. I went into a lot of detail, and I made loads of really nice pictures to help you understand it, because my god, this was so much work, but it was really rewarding in the end, in my opinion, so it doesn't matter. But I know you probably don't want to hear about loads of vector analysis and loads of equations, so let's not worry about that for the purpose of this video, and I'll just give you a very simplified rundown of what I've done. So with the Eagle simulation galaxies, I used specifically snapshot 28, and I used around 50,000 galaxies from that. So in the simulation, you get basically a box of galaxies, and I got rid of all the galaxies that I wanted to sample from the edges of the box and the ones that are too distant. This is because for my first step, I'm going to randomly select around 50 galaxies to host some mergers. And once I do that, I'm going to fiddle around with the distances and the positions and stuff later on. So I don't want anything that's too close to the edge of the box, otherwise I'm just going to get problems because there are no galaxies, you know, to the left or to the right or next to the merger on one side, and that's going to skew my results quite a lot. So what I did was, with these galaxies, I weighted them according to their mass. So a really high mass galaxy is very likely going to host a merger, and then a very low mass galaxy, like a dwarf galaxy, is not going to host a merger, which reflects real life because large galaxies have lots of stars, larger chance for it to have two big stellar mass black holes that are next to each other and then go on and merge. They're quite rare overall, but you know, like, a larger galaxy is going to have bigger chance of hosting a merger. Okay, I'm trying to word this correctly. So with the sample, the 50 galaxies that are going to host mergers, I created mergers initially with the same exact coordinates as the galaxies, so the same distance and same location. But now we've got these 30% distance errors and that credible region that I was talking about earlier. We want to use these to then add some noise to our mergers data. So we want to actually add those errors in and make it look like real life data that we would get from, you know, a bunch of mergers. Because when we measure something, it's not likely that we're going to have it smack bang in the middle of a galaxy itself. That would be really lucky, but with the detector capabilities that we have, that's just not possible. So I want to add in those errors itself. So from that, these mergers had between 0 to 30% error on the distance. This was randomly generated using a normal distribution, but you don't need to worry about that. And then with the credible region, I also did that randomly with a normal distribution, but I did it with vector analysis depending on, you know, the right ascension and declination, which you don't need to worry about. All that you need to know is that I added some noise that was informed by the current detector uncertainties. So here's the important part here. Now that we've got our 50 mergers and our 50,000 galaxies, if we have enough mergers, so ideally I should have made more of these, but for computing problems, I had to limit it down to 50. But ideally, if you have loads of mergers and that we're able to detect them with fairly good accuracy, with low uncertainty, and be able to pinpoint where all of their positions are pretty well, their distribution across the universe should match up with the galaxies, because we know they're in galaxies, and if we're able to figure out, you know, find out where they are with good accuracy, they should sort of look the same. So I can shift the galaxies further or closer, and in turn what I'm doing is I'm changing Hubble's constant. So this is why it's important that we know the true value of Hubble's constant here, so I can know how much I've shifted it by. And so in turn I can hopefully you know, do a couple runs of different values of Hubble's constant where the galaxies are more further apart or closer, and the mergers should match up best with the correct value of Hubble's constant, right? So for example, I've got two boxes here. The galaxies are in black and the mergers are in, I believe it's either green or purple or just a different color. And you can see with the picture on the left, we've got Hubble's constant being 50. And the mergers are actually, not the mergers, the galaxies are actually really far apart, and you can sort of tell that the mergers aren't really lining up at all. There's a lot of them are in just big white space, and that's no good. That means that, you know, Hubble's constant is too small, things are too far apart. Whereas with the one on the right, you can see that the mergers, there's quite a lot of them near this big cluster of galaxies, and you can sort of see that they're following the trend of the galaxy positions as well, which is a lot better and a lot closer to what we want. Admittedly, I had to write a couple paragraphs for this bit because it's quite difficult to explain just off the top of my head. I'm really sorry about that. So the way that I was able to sort of quantify this sort of best fitness is using what's called a cross correlation function. And this is just, I made this up myself, and it's just the distance probability multiplied by the location probability and a weighting factor. And I'll break these down right now. So basically the distance probability part, this is essentially, if you take one merger and it's at a certain distance, like, I don't know, 10 megaparsecs away. That's pretty close, but never mind. And then you've got a galaxy that's, you know, 10.1 megaparsecs away. What's the probability of that merger being from that galaxy? Well, it's going to be pretty high actually, especially if you factor in the distance error, you know, plus minus 30%, that's plus minus 3 megaparsecs. That's quite a high probability. So with the same merger, what's the probability of it being from a galaxy that's 100 megaparsecs away? Pretty low, it's very far away, and it's way outside of those errors anyways. So you can sort of do that for one merger with all of these galaxies, and so you'll get a couple galaxies that it's quite close to and will have a high probability, and a lot of them which should be very, very low probability. And so hopefully, if you're getting a lot of mergers which are close to a galaxy, you should actually have quite a high probability result here, whereas, like, for example, in that really spaced out case that I showed you with the picture, a lot of these mergers are actually far away from the galaxies, and so overall you should actually get a lower number at the end of this. And you can do exactly the same with the location. So if a this is aside from distances, this isn't factored into that. If, you know, a galaxy is in the same sort of position on the sky as the merger, it's got a high chance it's hosted that merger, whereas something that's on the other end of the sky is going to have a very low to near zero chance. And if you're finding that you're getting a lot of mergers that have, you know, a really close by galaxy, that's going to have overall a very high probability. So the weighting factor, which is the final part, is just the same as, you know, the mass weighting that I did when generating the samples. And so a higher mass galaxy just has a higher chance of hosting a merger, and you just need to factor that in once again. This did actually decrease the Hubble's constant estimate I got in the end, so it was really useful. So once I did that for one run for a certain number, for a certain Hubble's constant, I then changed the value of Hubble's constant. I think I started from 50, went up to 60, 70, 80, 90. Each run took about 1 hour. So with 5 runs just for one set of mergers took me 5 hours to complete, and that doesn't include the times when it crashed or when I had to go to sleep and stuff, and then the computer went to sleep and then it crashed again. Oh my god, that was so annoying, but I did get through it eventually. After that, I decided, okay, I've got one set of results. I'm going to generate a new sample of mergers and do that 9 more times, so I have 10 samples. So overall, it took me 50 hours of computing time to complete. That was quite painful. Right, so here I've got the results. I've got them up on my screen as well, but I'll show you really nice pictures on the video. So I managed to do eventually 10 samples. And from that, you know, I got a bunch of numbers for each sort of cross-correlation function value for every Hubble's constant that I did. And that was 50, 60, 70, 80, and 90. What matters is you need to plot them and see where the peak is, because that's where the highest, best fit Hubble's constant value is. With the plots, I made a plot of the cross-correlation function value, which I called big phi. And then on the x-axis, I've also got the Hubble's constant values. And you can see the data points are the numbers that I got. And then on top of that, I fitted a parabola onto it, which I found was the best fit for the data. I would have thought it would be a Gaussian, but I think I needed more data points in order to actually get that. I'm not really sure why. It happened with the person previously as well, who did the research project a year or two before me. So that's interesting as well. I'm not sure why that was. And then you can see on the peak as well, I've labelled it. And that's the best fit Hubble's constant value, which I got was 73.97 initially. And that's actually a pretty good value, I'd say. It aligns really closely to the supernovae values. We've also got some errors as well, which I think was +/- in the end. So the errors are quite nice as well, and they do encompass, I believe they encompass some of the CMB measurements, depending on which sample, but we'll get into that in just a second. So one thing I noticed when I plotted all of the data points with a line graph, which I think is at the start of my results, is that I noticed that there was a bias towards higher values of Hubble's constant, in which those phi values would end up being a lot higher. So if I show you the line graph, you can sort of see the low curves, or the low lines, which are, you know, the the yellowish red ones. They have lower best fit Hubble's constant values, but the graphs, the curves themselves, they're not curves, the lines themselves are much lower as well. Whereas with the ones with very high end best fit Hubble's constant values, which can go up to 81 actually with one of my samples. They got really high. They have much higher curves as well, which means that when I'm taking the average of all of these big ones are actually skewing the results even more. Regardless, I found that there was sort of a linear relationship between the best fit, the peak value, and that Hubble's constant value, which was, I think it was linear by like, the gradient was about 8. So I normalized them down, set them all to be the same sort of level, and then calculated a new average with that correction in mind. And I've then replotted it and got around 73.57, which is not a big difference compared to the original uncorrected value. But in terms of, in the context of determining Hubble's constant, this is actually quite a big thing. So I'm glad I did that, and it got me extra marks as well for my report, so just saying. Okay, so in the end, I got my final estimate as 73.57 plus minus 3.83. And of course, with the parabola, which is symmetric, my error, of course, was also symmetric on both sides. Other interesting things to note if you have a look at the report, sample 6 is the only underestimate. Every other sample that I collected was an overestimate of Hubble's constant, which you could once again argue, hey, this might just be a fluke. You know, you've got, I'd say, hopefully a 50-50 chance of things being an underestimate or an overestimate if there's no bias involved. Once again, we're talking about that, you know, that statistic significance aspect again. So I did a binomial test and I found out no, if you're assuming you're expecting a 50-50 chance of something, having a 90-10 split, you know, is probably, I think the p-value was really low, like less than 1. So I was like, no, there's definitely something going on here that I'm not quite sure specifically is, but I can at least say, hey, I've identified there is a bias in this data, which is pretty good. Also, if you have a look, samples 9 and 10 are the same. They look the same, they have the same phi value, something 0.44, I think. But I did go and check individually all the matrices that I used, and yes, every value is indeed different that I could look at. Like, I checked very thoroughly, and they are indeed different. It's just that for some reason they've all added up to be the exact same number, which is a really big coincidence. Right, I do think that now that we've got our result, we can quite concretely say that there is an overestimate going on, and given that most of our individual samples were overestimates, we can fairly clearly say that there is some bias going on here that we haven't quite dealt with just yet. What I'm thinking is that it's very similar to the real life estimates cases in that, you know, there are a lot more galaxies further away than there are closer to us from the merger. And so what I'm thinking is that when it comes to these probabilities, these really far away galaxies are just dominating the probability distribution, even though they're, you know, technically their probabilities are quite low. There's still quite a lot more of them, and that's causing a little bit of an issue with regards to the overestimates. One way I can think of that we can, you know, get rid of this is that we could just cut out the really distant galaxies. But the problem is when you get to really far out mergers, you know, plus minus 30% is quite a big amount, and you could potentially be scrapping the actual host galaxy, and you don't really want that. And if you were to do this, I think the best thing to do is to do this on a case-by-case basis with each of the mergers. But that's just going to take quite a lot of time for me, and I wouldn't be able to get that done within the span of my research project, which I think was 16 weeks. Given that, you know, it took an hour to do each run and 50 hours total, I just wouldn't be able to complete that. But it is food for thought for, you know, future work and stuff. But yeah, overall, despite that, I think it's quite a good estimate. It's quite close to 67.7, but it's also quite far away as well. And it's also important to note that if you look at the errors for my final, you know, average, it doesn't include the 67.7 as well, which is kind of a shame. but you know, that's life. I think the best thing that we can actually do to improve these results is to actually just improve the uncertainties. Because if you remember, this is all based on a simulation. I've generated these mergers based on the current limitations we have with gravitational wave detectors. If we just improve them, we should hopefully see smaller errors, and I can generate mergers that are actually closer to the host galaxy, and we should be able to get a better result, which would probably still have an overestimate, but just by not as much. But once again, improving detector sensitivity and equipment and stuff, it's a very difficult process. That's just going to take a lot of time and improvement. But once again, we are also seeing these improvements, and we're seeing new gravitational wave detectors being set up as well, such as CAGRA, and I think GOTO might also be a gravitational wave detector. I cannot remember, but we are seeing more detectors going online, and especially a lot more within the next coming decade as well. So overall, I think the standard siren technique is a really promising technique that, you know, despite the big uncertainties that we've got, we could potentially with more merger data, get quite good estimates for Hubble's constant. And I think overall, just the detection of gravitational waves and improving that will hopefully bring about some really useful insights into cosmology. So I'm all for it. I really love this research project, and it's definitely given me quite a lot of intrigue into gravitational wave astronomy. I know, I'm really interested in it now. Anyways, I think that about wraps things up. I'm really sorry if I gave you a headache, but I really hope that you also learnt something new and potentially even, you know, got some interest for gravitational wave astronomy now. So yeah, definitely do some research in that if you're interested. You know, we are seeing quite a few interesting new articles popping up every now and then on arXiv. So, you know, I definitely recommend, you know, reading up on some of the new papers and upcoming stuff on gravitational wave astronomy. There's definitely some interesting stuff going on in there. But anyway, that wraps up today's video. I hope you enjoyed, and I'll see you very soon.